Hi, we are going to sketch the graph of that given polynomial using only several steps. Now with regards to nonlinear functions, the graph of which will be curves, and they require only a minimum of 3 points. For linear functions, the requirement is a minimum of 2 points. So therefore, if you already have 3 or more points, then you may be able to sketch the graph of any given nonlinear function. Step 1, the very basic step which were already actually used before the use of calculus, and this is the determination of the so-called intercepts. For the y-intercept, you simply have to set x is equal to 0, and applying that to our function, we were able to determine one intercept which we will name as point A. That's very important, the name of the points, because we will be determining 3 or more points in here. So the coordinates of point A will be 0, 4. I am likewise encouraging you to at once simplify, or shall we say summarize the points, so that it will be easy for us to retrieve them any time. So I have made a simple table to illustrate such. So I have already identified point A and its characteristic, which is y-intercept. For the other intercept, we will set y is equal to 0, and we are about to solve for the x-intercept. But doing that will result into a 4th degree polynomial equated to 0. So to solve for x, naturally we will be solving for the roots. And since it's a 4th degree function, then somehow the process will be somewhat challenging for those who are well advanced in this particular matter. Then probably they've got an idea how to do it. But if ever you don't have any idea, then you may skip this part. But then take note, since it is a 4th degree function, then the maximum number of points of x-intercept will be 4. So it may be 4, it may be 3, it may be 2, it may be 1, or it may be nothing. So when you say x-intercept, it is a point where the graph will cross the x-axis. Alright, that's my advice. Skip. For anyway, we already have a point. So we only need 2 more points, and we may be able to sketch the graph of this particular function. In this step, we will not be determining a particular point, but we will generalize the behavior of our dependent variable, which is y, when x is very, very huge, huge positive and huge negative. Now, if you examine closely our function, x raised to 4 will be very, very much greater than 5x raised to 2 whenever x is very, very large already. It may be positive or negative, right? The result of, say, substituting any large value of x to x to the 4th will be much greater than when the same number is substituted to 5x squared. So the behavior of y for very large values of x will depend solely upon x raised to 4. Alright? So based on that premise, whenever you make x very, very large, that means x is very much greater than 0. So x is getting larger and larger, so it becomes more and more positive. Then the same thing is happening with y. On the other hand, when x is made more and more negative, x is very much less than 0. So that's x is getting more and more negative until such time that x becomes very, very large but negative. But our y will always be positive, because our governing expression in the function is x raised to 4. Remember that any number, positive or negative, raised to an even exponent will give us a positive value, isn't it? Alright, and we will set that particular thing right there for our reference later on. Then we will proceed with step number 3, which is the application actually of calculus. So therefore, at this point in time, I can safely say that calculus, specifically in this case differential calculus, may be applied to sketch the graph of any polynomial curve. Alright? So this is the point wherein calculus will be used in the determination of the so-called critical point. We will be able to digest later on what it means by a critical point. But right now, all you have to do is differentiate the given function. Now remember that one interpretation of a derivative is the slope of the curve. So if we are going to equate the slope of a curve to 0, then it means to say that we are trying to equate the slope to 0, meaning we are trying to determine a slope which is a horizontal line, because the slope of a horizontal line is 0. So therefore, this tangent line to the curve is simply a horizontal line. Alright? Now, why factor? Because we will be trying to solve for the values of x. And what are these values of x? They will become the x coordinate of a critical point. One critical point, therefore, has an x coordinate of 0. And then later on, we will determine the y coordinate. And if we can do that, then we will be able to specify already a critical point. Alright? And then, equating the other factor to 0, we will come up with 2 values of x. And naturally, they are going to be the x coordinates of 2 more critical points. Knowing them is the fact that we will have 3 critical points in the graph of this particular function. Okay, those are our coordinates of the critical points, and we will be solving for the corresponding y coordinates. But we knew already that an x coordinate of 0 corresponds to a y coordinate of 4, because we knew that already from our prior solution. And that is our point A, right? So point A is not only a y-intercept, but at the same time, yes, a critical point. Alright, that's it. For the second x coordinate, all you have to do is substitute that to the original function, because the concept is that these critical points are points on the graph of the function, and therefore any point on that graph must satisfy the relation. Alright, so that's why whenever you want to determine a point, all you have to do is test whether it satisfies the given relationship or not. Right, and then substituting the last x coordinate will give us the same y coordinate, and that will going to be our point C, our third point, and this is already enough to sketch the graph of the given polynomial. So watch out for part 2 of this particular video.